Welcome and thank you for joining today to the Geofabrics Academy. Today we will discuss detecting defects with liner integrity surveys. My name is Hackney and I'm the Mining and Environmental Manager here at Geofabrics. If you have any questions during today's session, if you could post them in the Q&A box, and I will try and answer as many of them as I can at the end of this session. Okay, so in terms of the content today, we'll start off with an introduction to electrical leak location surveys. We'll have a look at what defects in geomembranes look like. We'll then go into a bit of detail about the standardized methodologies used for electrical leak location surveys. I'll then have a short video to demonstrate what an arc test looks like with a conductive geotextile. We'll then have a look at some comparisons of how the use of conductive geotextiles compare versus other materials that can be used to conduct these types of surveys. I have a few case studies to share that demonstrate the uses of conductive geotextiles in electrical leak location surveys. And we'll finish off just looking briefly at some future innovations. So, electrical leak location survey, or shortened to ELL, they are surveys and they can be conducted on geomembranes that are installed in basins, ponds, tanks, or in waste pads, landfill cells, landfill caps, and other containment facilities. The procedures for conducting these leak location surveys, they are applicable for geomembranes that are made of a variety of polymers, and that would include polyethylenes, polypropylenes, PVCs, CSPEs, but also bituminous type membranes as well. Basically, any type of material that's sufficiently electrically insulating, and that's a brief description taken from ASTM there. At the bottom of the screen, this is just an example of what a arc testing method would look like. So you can see here an operator that has a detector with a probe walking along the liner that is placed on an earthen subgrade. There's a circuit that is completed once a leak or a hole is detected. That would sound an audible alarm and indicate there's a defect in the liner. But we'll go into that in a bit more detail as we look through the various different methodologies that are used. So the purpose of a leak location survey, it is primarily to identify and locate leaks in geomembrane liners and waterproofing systems. As we've mentioned previously, the applications include landfills, ponds, tanks, and containment systems. The method itself, it uses an electrical current and voltage measurements or the signal of those to detect breaches in the lining system. And there's a number of techniques available to do this depending on the site specifics, and there may be more than one technique that can be utilized to really ensure that all defects have been captured throughout the phase of construction. So the techniques include dipole surveys, water puddle, arc testing, and water lance methods, and we'll go into a bit of detail about what each of one of those entails. And the benefits of conducting the survey are that it actually pinpoints leaks with high accuracy, and then also that leads to minimization of excavation down the line and repair costs when it's identified that there's a leak. There's also a benefit in terms of environmental protection as well. You're ensuring that the liquid that is being stored, which in some cases can be contaminated liquid, is retained and it's not polluting the surrounding environment. Some of the limitations of the methods are that it requires a conductive subgrade as well as a conductive layer above in covered cases, or you can utilize an enhancement layer such as a conductive geomembrane or a conductive geotextile to enable that. And the the performance of the surveys, they can vary based on site conditions. So it's key that experienced surveys that understand the methodologies are used, and they can then calibrate the system or the survey according to the specifics of the site itself. What works on one site may not necessarily be the same procedure on another, just due to the local conditions. Okay, so geomembrane defects. This is just two very simple examples. The one on the left is a small hole you can see in a geomembrane liner there. So you've got a pen for scale. And this would be a hole or a defect that could occur during the installation phase of the geomembrane. So these are holes that can be identified before any cover materials placed on the geomembrane or it's filled with water. So this could be produced by dropping of tools, or they could be something sharp that's trapped in a tread of a boot that then causes these smaller types of plungers in liners, and sometimes not always visible by eye. You've got, typically black liners. I know there are white liners available with black undersides that make these sort of holes a bit more visible, but due to the size of these holes and the scale of some of the installations that these go on, these type of defects could be easily missed. And then on the right-hand side there's something that's a bit more large scale in terms of a tear and a defect, and this is some damage that has been caused by an excavator bucket. You can see the teeth there that have torn through the various elements of the lining system there. You can see the geomembrane at the base there with the 3 teeth marks in there, and then that's been overlaid. I think you can see a geonet in there, and then there's some geotextile that's been teared on top. So what's likely happened here is the geosynthetics have been placed, and then cover soils have been laid on top of the geosynthetic materials. They've been spread by machinery, and during that spreading process, the operator has somehow maybe gone too deep, or the spread in the layer has been quite thin, and that's caused teeth to damage the underlying geosynthetics. So including that barrier layer, which is the geomembrane, that's caused these significant holes in the teeth. And this isn't always going to be seen, because as the soils are being spread, this activity, these tears could happen underneath the soil, and it's not going to be apparent until a covered survey is actually carried out and can detect that this defect has happened. This is quite an old example here, but I think it's a good reference point. So this has been taken from GRI White Paper 34. And it's really a summary of from a paper there, and it's based on a survey of 300 geomembrane line sites with a total area of 3 million square meters, and it's categorized there in terms of what type of defect it is. So you've got defects caused by stones, by heavy equipment, by welds, by cuts, and directly by a worker. But then also in terms of each of those ways in which the defect has been made, the resultant size of the hole that's occurred. So some quite interesting data there in terms of both the total number of defects that are found, but also the size of those defects. So you can see from here that stones, which could be drainage aggregate on a landfill, for example, or underlying stones from subgrade that are maybe protruding, that have caused the majority of the damage there in terms of the percentage of defects that have been detected as a whole. I think the interesting thing to look at here as well is that if we look at the size of the holes and the type of damage that's been occurred on the geomembrane, and look at the size of the holes, you can see stones as a large majority are causing these smaller defects on the order of 0.5 to 2 square centimeters in the terms of the size of the hole. But then when you look at those larger types of tears that we saw previously that have been given by heavy equipment such as teeth and tears, There's a smaller proportion of those, but I think the important thing to note here is that even though they are smaller, the size of those holes are much larger. And what we'll see in a few slides' time is that has quite a big impact in terms of the amount of leakage that can occur. So there's an exponential rate of increase of leakage depending on the size of the hole. And there's an example that we'll see in a few slides' time of that. Okay, so in terms of the liner integrity surveys, there are standardized methodologies, and the American standards for test methods, ASTM. They've developed these suite of test methods to standardize how a leak location survey is carried out. So you have a guide, ASTM D6747, and that's a general guidance that will allow you to select the most appropriate methodology for conducting the survey. And we can split that into two different types of methods. So we can do surveys on geomembranes that are exposed, and there are 4 methods there. And there are methods in the situation once the geomembrane has actually been covered. So that may be with water or with earth. We will look at these in a little bit more detail just to look at some of the pros and cons of each. So we'll start off with ASTM D7002, 7003. So these are preferred for bare non-conductive geomembranes. These methods have sensitivity, so this is the size of the hole that they can detect. So these methodologies can detect leaks on the order of 1 millimeter in diameter. The pros of this is that the test is relatively quick, but on the flip side, if we look at the cons, it requires a water source, so you need to be able to have sufficient water available. So in remote locations, you may have to bring in water trucks to be able to do this. Because we're using water, it needs to be contained within the survey area to keep the area isolated. You wouldn't use the water puddle method on a slope because you're relying on a puddle of water to transfer that current through the system. So on a slope, obviously, the water would not generate a puddle. So in that case, you would have to use the water lance methodology. So on steeper slopes, you'd use a different method because of the nature of the water moving down the slope and not being able to travel through a hole. You need that continuous flow of water to enable it to penetrate that defect, so it can then the current can then be detected to pass through the defect. So as I mentioned, when conducting this method, the survey area needs to be isolated. So you don't want the current running in various different locations. So sumps and batten strips need to be isolated. And I guess the other thing to point out here is that holes on wrinkles may not be detected on non-conductive geomembranes. The operator can push the wrinkle down, and that's about initiating and creating intimate contact between the geomembrane and the conductive medium underneath. If there's an air gap, such as in a wrinkle, and you've got a defect on the top of that wrinkle, it's not going to allow the electricity to arc and connect with the conductive medium underneath. So there's cases whereby if wrinkles are not pushed down or they are too high, that holes or defects could be missed. Okay, so that was wet methodologies. There are also dry methods for conducting leak location surveys. So ASTM D7240 is a specific method for conductive backed geomembranes. So this is typically HDPE and LLDPE. A co-extruded layer of high conductive material can be extruded on the underside of the geomembrane. So this is usually conductive carbon black. It's I don't know, maybe a 20% 20% by weight content of carbon black that's co-extruded on a thin layer on the underside of the geomembrane. So that creates that underside of the membrane, the whole of the underside of the sheet has that conductive capacity. So if there's a defect throughout the membrane, the electricity will pass through the hole and connect to that conductive underside of the membrane and enable leak detection. So it's a dry method, as I mentioned. It can detect small leaks. The membrane must be clean and dry in order to perform this method. So yeah, benefits are there's no water required. So remote locations, you don't have to bring water in. And the other thing is that you can perform this on flat and sloped constructions, but also vertical faces as well. You're not losing any water. Water has to penetrate through the defect in this particular methodology for the survey to occur. And also, if there's wrinkles, there's a benefit here. The fact that the conductive layer is in intimate contact with the membrane, it's part of the sheet. If there's a defect in the wrinkle, because the conductive layer is on the underside of the sheet and part of the product, it will enable a defect in an area such as a wrinkle to be detected. The cons are that you can have a conductivity gap. So when you fusion weld or extrusion weld the membrane, you're potentially removing that conductive layer on the underside of the membrane. So there's certain procedures that need to occur to enable continuity between the welds. And similar to the previous method, moving on, there's the arc testing method. So using similar equipment, where it's a separate ASTM. So this is ASTM D7953. But again, this is a dry methodology, and this is a method whereby which arc testing is completed with this type of equipment in a dry situation. And this is where you need to have a conductive medium underneath. So that could be a moist GCL. It could be a subgrade that's got sufficient conductivity. It could be a geotextile underneath that's got sufficient moisture or some wiring in there, or something such as a conductive geotextile that enables that conductive layer underneath for the survey to be completed. So pros of this method, again, that it's quick, there's no water required. You can do this on all types of slope inclination. But I guess not so much of a benefit here is, again, you've got the gaps that can potentially limit arcing. So if you've got wrinkles and they're sort of higher than about 3 centimeters, again, you've not got that intimate contact between the geomembrane and the underlying conductive material, which then results in potentially missing a defect in the liner. So you can see some examples of arc testing being completed on the pictures there. Moving on to, so all those previous methods we've just discussed are on bare geomembrane, on membrane that's not been covered. It's just been installed. You would do a survey once the installation has been completed to ensure that any defects during construction have been detected. These methods that we're going to discuss now are covered surveys. So this is once the liner has been installed and any other geosynthetics are placed above that. There would then be maybe drainage aggregate in the situation of a landfill cell, or if it's a cap or another type of project. Once you have cover soil or water that's placed on top of the lining system, this is where we look at covered surveys to check whether those types of damage we saw earlier, such as with the excavator bucket that are unseen, have occurred. So this enables any damage to be detected during that sort of final phase of completing the system. So the dipole method, in terms of when soil is placed on top of the lining system, this method's conducted according to ASTM D7007. So the cover, it could be soil, gravel, concrete, sand, any conductive medium really. It's not as sensitive as the bare test in terms of following this particular methodology. So just as an example, a 6.4 millimeter diameter leak could be detected if there's 600 millimeters of cover. But again, that's very dependent on site conditions, moisture, conductivity, depth of cover, etc., how well it's isolated. That all influences the sensitivity of the actual survey. So yeah, as I mentioned, the material in the membrane, it still needs to be sufficiently conductive to be able to complete that circuit. And you can see a diagram on the top side there, on the right-hand side of what a dipole method with soil looks like in terms of completion of that circuit and how a leak's detected. And as I've mentioned earlier, survey areas need to be electrically isolated. So usually perimeter isolation trenches are left, which is preferable during placement of fill material to leave a trench that's not filled, rather than filling the whole site and then digging a trench, which can potentially cause damage of the liner during that filling stage. If it's known that one of these surveys is going to be carried out, it's a good idea to leave the trench and not fill a certain area to allow this isolation to occur. So voltage measurements, they'll be taken in a grid pattern. Again, in terms of holes on wrinkles, they may not be detected, but also importantly with the soil cover method, data is recorded, so that enables review of the data and reporting of that data when it comes to doing a final report on the survey. Using the same method, there's also a section when the site is water covered. So when you, such as a pond, dam, etc. So the survey, it'd be set up in a similar method as a cover soil method. But what happens here is that as you pass over a leak, there would be an audible signal to indicate that there's a leak in the vicinity there, which you are surveying. It's a bit more sensitive in terms of diameter of the leak because you've got the hydraulic head of the water providing better hole contact, allowing the transfer of that current through the hole. But one thing to note here is that it's not always going to work in every single type of chemistry. So an example here is that if you're doing a survey in brines, for example, or there were poor boundary conditions, you might have to employ a different geophysical survey to be able to enable detection of holes in specific chemistries. So probably more ideal for water type storages. I guess one downside of this particular method is the lack of reporting requirements and transparency. So making these methods auditable is key. How solid is the data and has every potential hole actually been picked up? So I think this is where there's been a newer method in this area that's been developed by STM, and this is STM 8265. And this was drafted and adopted to update procedures and shortcomings of the dipole method to enhance the method in terms of sensitivity and but also provide transparency. And the aim of this method was really to be able to enable as close as possible as to a zero leak condition. So yeah, there's a number of procedures within this that really allow for a high level survey to be conducted with accuracy and reporting and auditability. And also there's a focus on safety as well. So obviously conducting these methods using very high voltages, but currents need to be limited because significant current is what can cause, burns or even death. We're dealing with electricity here. So again, there's an element here to safety in terms of performing these surveys. I think the takeaway from looking at both bare and covered methodologies is that it's the combination of both of those that really ensure the integrity of the lining system. You would install a geomembrane, perform a bare survey, and that would pick up those smaller type of defects that we saw in the table, where they could be caused by, there's a large proportion of defects that are caused by stones. And then that would follow once the liner has been covered with soil or gravel, or the covering medium, to then do a covered survey, and that really covers both aspects: any damage that could have occurred during installation of the membrane, and then any damage that would occur that's not seen or observed during the final phase of the installation. Got a short video here, and this just demonstrates an arc test that's been carried out. So there's a non-conductive geomembrane on the underside, conductive geotextile placed in the middle, and then a non-conductive HDPE geomembrane placed on top. And that geomembrane has got a number of predetermined holes drilled in there, 5 millimeters, 4, 3, 2, 1, and it just shows how the arcing occurs through the defects onto the conductive membrane, conductive geotextile in the middle. You can see the arcing there, traveling through the 5 millimeter size hole. And then the holes get smaller and smaller, just showing how sensitive this method can be. You can hear the audible alarm, so as well as the arcing sound that you can hear, the holiday detector or the arc test will also provide an audible alarm to state that the defects being detected. So this is just showing that 100 millimeter overlap is sufficient with the conductive textile to enable these surveys still to be carried out. This continuity through the overlap there, through the full range of defects down to 1 millimeter in the example there. Okay, so I'm going to talk a little bit about conductive geotextile. There's a video just playing on the right hand side there. It's just in a dark environment. You can just see that arcing again, how the power directly jumps, how the electricity jumps from the arc tester to the conductive material, and you can see a bit of a circuit within the material itself there. So, in terms of conductive geotextiles, Bidim C is a product made by Geofabrics, and it was the world's first commercially available conductive geotextile. So it's a highly conductive layer that's blade coated onto Bidim geotextile, so it can't peel off. It's embedded within the surface fibers of the fabric. The conductive geotextile Bidim C provides that conductive medium below the geomembrane. It can be placed between the subgrade and the geomembrane, or it can be placed in between liners, like we saw in the previous video, in a double line system. And that might also include a drainage composite as well, so you can have the conductive geotextile placed against the geonet or the conductive geocomposite to first detect leaks, but then if there are leaks further down the line, the composite can drain the liquid away. I think one thing to note with conductive geotextiles is that they shouldn't be placed between a GCL and a geomembrane, because that interrupts that composite action that GCLs and geomembranes as a composite system have. You're interrupting that behavior, so that wouldn't be recommended. As we saw in the previous video, it's easy to install. There's no special bonding required. It's just simply a minimum of 100 millimeter overlap, and you would roll it out like any other geotextile. You can also place it upside down as well, so the electricity will still pass through the structure of the geotextile. So whether the conductive side is facing up or down, it will still you'll still be able to detect holes as small as 1 millimeter. A further benefit as well is that conductive coating. It has some grittiness to it. You know, the conductive material in there, it's quite gritty, and that actually gives elevated frictional properties to the material as well. So I've got an example I'll show you in a few slides time in terms of what the frictional properties of this material is. But again, it's something that could enable this type of material to be used on slopes as well, because it has that elevated frictional performance. The material, the conductive geotextile, it has a specified conductive value that can be tested. So when we look at data sheets, typically for these type of conductive materials, it's the actual measurement is surface resistivity. So resistivity is the inverse of conductivity. So the lower the surface resistivity is, the more conductive the material is. So these type of geotextiles have less than 5,000 ohms per square in terms of surface resistivity, which is pretty conductive material. And as I say, that can be tested. There's ASTM methodologies that allow that test to occur, so that you can verify the material and its level of conductivity throughout the footprint of the project, and test it like any other method that you would for CQA, such as other index type tests. Also, the carrier of the conductive material, the Bidim, the geotextile itself, it also has additional function. It can provide cushioning, and it can also provide a filter or a separation layer when placed against a geonet. It's still permeable, it's still porous, so it has a number of functions as well as being conductive. It can serve those other functions as well. So some benefits there. Okay, so as we've seen, small holes in a geomembrane, they can cause significant leakage in the lining system when there's a hydraulic head acting on it. And as we saw earlier from that example from GRI, there's always holes that are likely to occur. So yeah, just highlighting that a good CQA program is crucial in the installation of a quality geomembrane system that includes an electrical leak location survey to enable as close as possible to leak free as possible. So in terms of defects in membranes and what that translates to in terms of leakage, there's two tables on the bottom of the slide here. On the left-hand side, so no geomembrane is completely impermeable. Liquids, gases can diffuse through these membranes at a molecular level. So there's always some level of leakage to be expected. So, the example here is diffusion through a HDP under different hydraulic heads. So, for example, you can see when you have a water head of 3 meters on a geomembrane, that pure diffusion mechanism through the membrane itself without any holes, that's still going to result in something on the order of 80 liters per hectare per day that would pass through at a molecular level. But it's actually the defects that are expected, and what can then lead to significant leakage. So if we look at table 2 on the right there, we can see various examples of a defect diameter. So you've got 0.1 millimeters, 0.3, 2, and 11.3 in terms of pinholes or holes. And then depending on the water depth on top of that defect, what that means in terms of how much liquid can pass through that hole. And you can see it's an exponential rise in terms of the leakage rate through the defect. So again, if we look at a 3-meter head of water acting on a defect, if there was just purely a pinhole of 0.1 millimeter there, purely just through that one pinhole, by calculation, it would be expected to have a leakage through that one hole of 6 liters per day just through that pinhole. So if you've got a number of those pinholes over a hectare, you can start seeing significant leakage. As that hole diameter increases, if you were to get 0.3 millimeters under a 0.3 millimeter hole under 3 meters of head, the leakage through that one hole, would be on the order of 500 litres per day, and all the way up to something that's still not significantly large compared to some of the examples we've seen. A hole of 11.3 millimeters in diameter, it could be expected that 40,000 litres per day would travel through that hole. So you can now see the significance in terms of leakage and detecting these defects to enable containment of the liquid that's being contained within these systems. Okay, so electrically conductive geotextiles are just one type of material that can be used to enable these types of surveys under membranes. So traditionally, or other options are that the geomembrane placed on the subgrade could also enable a survey to be carried out, but there's just some comparisons here in terms of what a survey with a geomembrane against subgrade versus, using more conductive material such as a geotextile would be. So strengths in terms of using the subgrade as your conductive medium is that the clay is already there. It's below the geomembrane on site. The clay and geomembrane can be a good composite lining barrier, and you can still achieve high conductivity of that underlayer when it's being constructed correctly. Some weaknesses may be that you still require that intimate contact between the geomembrane and the clay to detect holes. Remote conditions in some areas in Australia, it can be quite hard to retain that moisture in the subgrade. There's evaporation that can occur, desiccation that can happen in the subgrade, so that could impact the conductivity of the subgrade underneath the geomembrane. And again, as the membrane gets hot during the day, wrinkles form, and you're losing that intimate contact, but also allowing evaporation to occur and collect within those wrinkles, and again desiccate the clay underneath the wrinkle as well. So again, not enabling a good conductive medium beneath the membrane. So it requires high quality material, and it could be tough to construct. And another sort of subgrade weakness is that that conductivity is only really known when it's finished and constructed and the line is in place. So there's a little bit of unsurety in terms of, is the full footprint going to give me that full connectivity and conductivity that I need? So with a geotextile or a conductive geotextile that's placed on the subgrade, beneath the subgrade and the liner, it's simple to roll out, as we've seen, with that consistent QA'd conductivity value. It's higher in terms of conductivity than the clay. It'll detect across certain wrinkles of certain height, and it's got that additional benefit as well. So if there are any ruts or stones in that subgrade that could damage the membrane, the conductive geotextile has that secondary function of being a cushion to, again, as well as detect any potential leaks, it can always limit any damage that can be given by those potential stones and protrusions as well. There are other conductive materials that can be used to enable the survey. So in addition to conductive geotextiles such as Bidim C, there's also conductive geomembranes themselves that can be used on their own. So it's as I've mentioned earlier, it's co-extruded as part of the geomembrane itself. So it's a thin carbon layer on the underside of the geomembrane. So it's typically cheaper than a conductive geotextile alternative, and it's a single layer installation. You've got higher probability of leak detection on a wrinkle because the conductive layer is part of the membrane itself. There's no detachment, there's no air gap, and that clay GCL or HDPE composite action can be maintained because there's nothing in between the subgrade or the GCL and the HDPE. I guess some weaknesses in that respect is that it's usually limited to HDPE and LLDPE geomembranes, that conductive layer that can be co-extruded onto membranes. You still have that conductivity gaps at welds, and in some cases, there's patented procedures to enable that that's only available with certain membranes. And another thing to consider is that increased carbon black layer on the underside of the geomembrane. There have been studies that have been conducted that indicate that increased carbon black layer as part of the membrane itself, it could potentially impact performance. It can interact with the stabilizer packages, the antioxidants, which can potentially impact on what the durability of the liner itself looks like. So it'd be recommended to do specific immersion studies just to ensure that higher carbon black layer is not impacting the longer term performance of the geomembrane in any way. Another thing to highlight here on the bottom, there's a zoomed in circular defect from one of the videos earlier. On the left hand side, if you consider that to be a conductive geomembrane, the electricity can only connect with the conductive layer on the circumference of that defect. But if you've got a conductive geotextile underneath, you've got that full area of the defect where the electricity can travel to. So there's not as much area there is on the right, and I don't know if there's dirty geomembrane or there's less potential for that defect to be picked up on the left than on the right, just purely down to conductive area available for power to pass through. Okay. I mentioned earlier that Bidim C, due to its coating and its grittiness, it actually has quite impressive shear strength properties. So there's an example here. This has just been a shear box test that's been conducted over 100 to 500 kPa normal stress, and that's the conductive surface being sheared against just a standard geotextile, and you can see peak friction angles achieved on the order of 34 degrees. So that's quite comparable to a structured textured geomembrane in terms of the friction that can be enabled there. So, if you are placing these on slopes and you want to have some friction available, and as I say, you can place this material either conductive side up or down. You've got some friction available there as well to incorporate into the stability risk assessment. So another benefit. Okay, so we'll look at some case studies as we're getting towards the end of the presentation. So these are focused on the use of Bidim C of conductive geotextiles. So there's an example here of a project done for SA Water at the Morgan Water Treatment Plant. This was a $15 million upgrade to meet future demand in a regional area to supply 130,000 homes. So part of the upgrade included this 30 million litre water dam that you can see on the right there. The membrane in this particular case used in the dam was a Cooley Oasis EIA type membrane. And there were other elements in this system as well, including cushion geotextile and Flownet. But also, as I mentioned, the Bidim C conductive geotextile underneath the EIA liner, and that enabled leak survey to be carried out post-installation to ensure that there was no leaks in the liner. So the pond's been commissioned in use and supplying the homes with water, and the asset owner is happy that for the next 30 years they've got a well-designed and leak-free pond. Another case study here. This is from a mine site in southern Australia. So in this particular case, the mine site had aggressive wastewater, and that aggressive wastewater needed to be contained. So there's a robust design, including a CSPE as the primary liner, an A34C conductive geotextile underneath the primary liner, and then a leakage collection layer composing of a geonet underneath that was placed on the compacted clay layer. So the target in this commissioning was to get a seepage rate close to zero. So that was enabled by a high sensitivity leak location survey. The CSP is not conductive, so the A34 enables this survey to be carried out, and that resulted in a high quality storage asset with assured commissioning and avoiding risk of delays when handing it over to the operational department, because it can be assured that there's no defects in that liner by the survey that's being conducted. And then a third example here that I can share is this is in the coal seam gas industry. So this particular example was construction of brine waste tanks in 2017. So there was two large tanks. The tank dimensions are detailed there on the right. So these large footprint tanks constructed with a double line system to contain brines. So this include a primary liner, a geonet to collect any potential leaks, with Bidim C placed on top. In this particular case, there was also a secondary liner underneath the geonet. And then, because this is the first time the operator used the Bidim C, they also did a sort of a benchmark test with the traditional leak methodology underneath the secondary liner. So this included a copper wire system with the geotextile sufficiently wetted to enable a survey. So what that showed was that the traditional, testing was undertaken on that secondary liner first by wetting the textile, as I mentioned, but that added cost and complexity because you have to bring, water and spray and prevent any evaporation so that the survey can be enabled. And then with the Bidim C under the primary liner further down the construction phase, that utilized the properties of the Bidim C and allowed a different type of test to be conducted with the ARC methodology. So that was done dry and no water was required, and it allowed the team to assess both methodologies of conducting the liner. So some lessons that could be learned from those two surveys that were conducted. So with the traditional methodology, testing had to be performed after wetting because of evaporation in this particular location. There was significant volumes of water required. There was possibility of false readings due to the water used for in the wetted system, and it required multiple operators in that older methodology, and copper wires present a bit of a trip hazard as well. But on the other primary liner, when the conductive geotextile was utilized, there was multiple operators that could run simultaneously. So that's obviously benefit in terms of enabling quicker surveys on larger footprint projects. Just to finish off, got a few examples of future innovations here. So, we have a conductive type textile so that's the hardware in the system. But here is an example of using that hardware, using that conductive textile material to link with some software, and potentially further down the line, by having the appropriate software developed, this could enable a live view of leaks. So if you imagine this to be a large pond or an asset, if there's a leak that develops, by having this type of system in place, you could have a visual and audible system which could actually tell you where the leaks occurred, and that could enable easier and more appropriate repair. So this technology is being worked on, and it's again something for future innovation. We have the hardware side in terms of the conductive material, and then the software side that enables these type of measurements to occur. So something interesting for the future there. And another example here is, we've supported PhD studies in this particular space, and this is one particular example where it was investigated how the conductive geotextile could be used as a sensor itself. So this particular study was, the response of these type of geotextiles under pavements to, as a detection. So that could be detecting number of car passers, by detecting any defects in the road, by detecting sinkholes, for example. And that's related to this piezo resistivity. So as the material is strained, that then results in a change in measurable resistivity. And again, when that's hooked up to appropriate software and detectors, that could potentially enable these type of systems to be embedded within infrastructure in future. So again, just using the material as a sensor itself by utilizing the resistive properties of the material. So again, something interesting for the future. And that completes today's Academy session. So thank you very much. And if there are any questions, I'll hold on for a minute and answer any questions that have come up. So thank you very much.